I'm Ross. I'm going to try and help you out here with this integral problem. The question got a little messed up, but I think I figured out the integral you want to work with. It looks like it's supposed to be the integral of e to the x dx with respect to x from 2 to 4. So a definite integral, which it needs to be for this problem. And then you're talking about a right endpoint method. This is another name for right-hand Riemann sum is how I usually think about it. And so, and also you have n equals 5, and just keep in mind that n is the number of sub-intervals we want to divide this thing up into. So I'm actually going to start with the last part first. I'm going to start with the sketch a picture piece because I think that might help you to understand better where the answer comes from, and you need the picture anyway. So the first thing that we actually need to do is split this thing up into subintervals, which is the 5. And so that means I'm going to come down here to the graph I've drawn. This is e to the x. E to the x would actually be a lot steeper, but we'll use this for now. And I'm going to split this up into 5 pieces. So that means that's not quite right. That means I'm going to need to draw 4 little lines here, kind of spaced evenly. And only 4 lines because that's going to give me 1, 2, 3, 4, 5 intervals. So I've broken the 2 to 4 up into 5 different pieces. The next thing I need to know is where all of those different pieces land, and so how far apart they are. Well, that's pretty easy to find. All I need to do is figure out, first of all, how far apart are 4 and 2 to begin with. You subtract those, you get 2, so 2 total units. And I want to split that up into 5 pieces for the 5 subintervals. So you divide 2 by 5, and that's going to be 0.4. So each one of these smaller subintervals is 0.4 units wide. And so to get to this first little mark here, right, if you add 0.4 to 2, you get 2.4. And then another 0.4 would get you to 2.8. And then 3.2, and then 3.6. And then if we add 0.4 again, we get to the 4, which we should. And just to go ahead and do this, I have a table set up over here, which we're going to use. I'm going to go ahead and just copy all of those numbers over because those are going to be our x values when we go to complete the right endpoint method here in a minute. So 2.8, 3. Ooh, that's not a 3. It's a funky 3. 3.2, and then 3.6, and then our 4. Okay, and then the next piece I want to do is go ahead and draw what the Riemann sum would look like, or the endpoint method would look like. And to do that, I'm going to go ahead and draw the points here to show where each of these points would be lined up with these x values. So at each of these values of x, just drawing kind of crappily, but drawing all those points. Those points are where we're going to base our picture off of. When we draw a Riemann sum or this endpoint method, all we're doing is drawing rectangles to help us estimate the area that's underneath the curve, which is all an integral is. When they ask you for this integral, technically they want you to cut off this little blue piece here under the curve, and they just want to know how much area is underneath that. And there's a straightforward calculation you can do to find that. But a Riemann sum is a way to estimate it. And to estimate it, you draw rectangles, because rectangles are really easy to find the area of. It's just length times width. So where do those rectangles come from? Well, in a right endpoint method, what that means is you start at the right-hand side of the graph. So you start all the way at the furthest point. You start on the right hand, and then you just draw across, so toward the left. So in a right endpoint method, you're drawing toward the left until you get to the next point right there, and then you just draw all the way down. And if I draw the right hand side to match that, that is not a perfect rectangle, but that's going to be my first rectangle. So if I find the area of this guy, I will have sort of an estimate of that piece of the graph of that area. Now hopefully you can already see that's not going to be a perfect estimate, because I already have, all this green part that's not even underneath the graph. So I'm adding more area than I want, but that's part of why this is an estimate. All right, so that would be my first rectangle. And go ahead and notice at this point, what the length and width would be. Because to calculate the area, that's what we would need. Well, the width down here, we already actually talked about that. That's this 0.4, right? This width would be 0.4. And then the height, this piece, would actually just be however far up we need to go to get to that point. And that's actually just going to be the y value that we get for that point, right? Whatever that y value is going to be the height of the rectangle. Well, to get that rectangle, remember this function is e to the x. All we would need to do to get that is plug in the x value we care about. And that was this first point we used. So the height of this rectangle is going to be e to the 4th power. We just plug in the 4. I'm not using the 3.6 because that point is not the highest it gets, right? I have to go all the way up to the 4. And so e to the 4th would be the height of that first rectangle. In fact, that would be the first point, or I guess the last value over here in my table. And I don't care, I mean, e to the 4th is some number, maybe 9 or 10 point something. I don't care. It's not worth it to do the decimal now. You can do it later. Okay, so moving on. So let's go ahead and do the next rectangle. So to get the next rectangle, you start at the point, the next point over, which is this one right here. And then you do the same thing. You move over to the left, draw down, and then you repeat that process over to the left, draw down, to the left, draw down, to the left, draw down, and then you're at a point. So don't keep going, right? Don't keep going to the left because then there's no point to draw through. You stop once you hit the beginning of your interval, which is 2. And now just to make this point again, notice, I mentioned that an integral is estimating the area underneath the curve, which we'll call all of this purple, right? So that's the true area. But notice we, with all these rectangles, have all of this orange area that's included in those rectangles that's not included in the pink. So this estimate is going to be over what the actual area is. Okay, so now coming back to that idea of finding the heights, for each of these rectangles, we would just plug in the values of the subinterval markers, right? These x's. So I'm going to fill in this table to match that. So the height of this next rectangle would be e to the 3.6. You just plug that in, plug 3.6 into your function, and then e to the 3.2, and then e to the 2.8 would go here. And again, these would all be some decimal, but I'm not going to bother plugging those in right now. And then e to the 2. But one of the key pieces to these estimates, to your endpoint method or to the Riemann sum that it's called, and just for reference, that's spelled R-I-E-M-A-N-N, Riemann sum. One of the key points to this is now that we have all these numbers, right? We have 6 numbers, but we only have 5 subintervals. And that means one of those numbers is not going to be used. So let's make sure we understand which one that is. So for this very last rectangle, we're using e to the 4th, right? That was our height. The next one was e to the 3.6. And then the next one would be e to the 3.2. And then e to the 2.8. Oops, it's messy. E to the 2.8. And then this last one would be e to the 2.4 right here. That means e to the 2 is not getting used. Because we ended at the end of that interval and we didn't draw a cross again, that very first number is not used. And that's not a coincidence. Anytime you use a right endpoint method or the right Riemann sum, the very first value, the left-hand value, will not get used. If instead you did a left-hand estimate, the right-hand value wouldn't be used for a similar reason. So now we need to go back and do all the math behind this to figure out the estimate for your area. Thinking in terms of the rectangles, all we would need to do is do the width times the length over and over again. And so again, every single one of these intervals has a width of 0.2. So I would do 0.2, and I'm going to start at the left-hand side right now, or not 0.2, 0.4, excuse me. So 0.4 is the width of the first rectangle over here, and its height is e to the 2.4. And then our next one is, then we're going to add on the area of the next rectangle. The height would again be, or the width would again be 0.4, and then the height is e to the 2.8. And again, we're multiplying those because the area of rectangle is length times width, or width times height, whichever you want to think about it. Now, instead of looking back over those rectangles, let's just connect this to the table here. The subintervals are each 0.4, right? And that's coming from the distance between each pair of subsequent values. So to find the width of the subintervals, all you have to do is subtract each of these numbers. It's not letting me write anymore. 0.4 and then another 0.4. So even if those intervals weren't equal, you could just subtract them to figure out how far apart they are. And then in this right-hand sum, every one of those widths is getting multiplied by the next y value. So the first is multiplied by e to the 2.4. The next one is multiplied by e to the 2.8. And then we just keep going until we run out of values. And it should end up that you don't have any leftovers. If you have leftovers that you didn't use, something went wrong. So to finish up our equation here, our expression, that means we would have 0.4 to the, or times e to the 3.2 plus 0.4, sorry for my crappy handwriting, times e to the 3.6. And then finally plus 0.4 times e to the 4. And all of that together, when you finally plug it in and get your decimal, that should be about 57.7, or excuse me, 0.279. So that is the approximate area, that pink area under the curve. That's the area we're approximating. It isn't true because, like we said, we had some overestimating with those rectangles, but that is the estimated area you would end up with using this right-hand endpoint method or the right Riemann sum. So I hope that not only answers your question, but also helps you, if you need to get some more context around how these sums work, how these estimates work, and how they connect to the integrals as well.